Good morning. So we'll start today's lecture. We talked about meshing the other day. So now I know you have some practical experience with that after the first week. You've started your tutorials. I know most of you have done up to the second tutorial. Some have progressed up to the fourth tutorial, third and fourth tutorials. That's good. I've also uploaded the fifth tutorial today, which is the CFX tutorial. But doing that is not compulsory, but you may find it useful if you find time. It will take like one more hour of yours to do the fifth tutorial, but you don't have to use that tutorial for your assignment. So tutorials 1 to 4 will cover the material for your assignment. So fifth tutorial is for additional knowledge. You may need it for your projects, or you may need it for your you will need it for your master's level design of fluid systems, but that's 1 year away anyway. Okay, this is where we stopped. So for the meshing, because you need to know a little bit of meshing for the tutorial 4 and for your assignment. So when you mesh, you can give a maximum or a minimum size. These are the largest cells here. These could be the smallest ones. So you can fix them in your code, so that so that you won't have really large cells, or that you don't have really small cells. And when you mesh, it's a very good thing to do, a very good practice to do. Mesh the faces first, and then mesh the interior. Okay, so if you take this one as your domain, you take the surface. You mesh the surfaces first. So this surface, that surface. So you do all the surfaces first, and then you can do the volume inside afterwards, because you need a good mesh at the walls, because you in most of the cases you need to apply wall boundary conditions, or inlet boundary conditions, or exit boundary conditions. So at those phases, you need a reasonable mesh to accommodate whatever you have. For example, for whatever physical properties you have. For example, for the walls, you need a boundary layer. For the inlet and exit, you need a good resolution, so that it will pick up the inlet or exit velocity profile properly. So therefore, you need to control the mesh in the surface, on the surfaces first, and then do the volume mesh. And then also you can give what you call a growth rate. A growth rate is defined like this. Now, for example, in here, you can see that the size of the grid cells are increasing along that line. That means it has a growth rate. So usually you can have a growth rate of about 1.1, or maximum is a 1.2. That means if you go along an edge, the cell size of the second cell is 1.2 times the cell size of the first one. Okay. So when you have a third cell, that third cell will be, if it is 1.2 times, if the growth rate is 1.2, The third cell will be 1.44 times the first one. So that's a fairly, it's nearly 1.5 the first cell. So it's a fairly high growth rate. But because it's the order, the growth rate is it's not just linear, it's multiplying. You can give a linear growth rate as well if you wanted to. And you need to pick up the curvatures well for a good resolution. So for example, if you have an aerofoil like this, you need to have a good resolution in here, because the physics here is you have fast or acute physics there because of the shape. The directions of the flow change, the vector directions, vector magnitudes all change rapidly here. Here, not as rapidly as in here. So therefore you need to resolve the curvatures well. You need to pick up the curvatures well. So for that you need a good grid resolution near these edges and curvatures, not just the boundary layers. So if you envisage any fast or abrupt behavior in your flow field, you need to pick up that behavior using a good grid resolution. Remember that. And also proximity. Now in here you can see that there is a void in the middle, which is not coming into the calculation. So if you have like really big cells here, one cell can accommodate that void here, meaning your physics will be completely wrong, because so if you have a void like this in the middle, you need to have a high grid resolution around there to accommodate the physics there. So when you set a tolerance for set a tolerance, the grid will remove the details that are smaller than the tolerance. So keep that in mind. So you give a minimum cell size. So anything smaller than that minimum cell size will be ignored by the mesh. Sorry, which one is better? Is that okay? Huh? Good? Yeah. So there are some local mesh controls. What is icing? What is icing is now here, because in this area you have a nice cube here, basically rectangular. So you can have rectangular cells here, but here you can't pick up. You can't have a good rectangular cell. Therefore, you want to use a you want to use TETs as grid cells. And for example, in here. So in here you give a number of fixed within the body, okay? And then you can have face sizing and edge sizing. So when you do face sizing, you define the number of cells on that face, and edge sizing is you define the number of cells along an edge. So that is very true for a that is very true for an edge. Now in this edge, you define a number of cells, and that is fixed. So on a face, you define a number of cells on the face, then that is fixed. And in a body, you define the number of cells that encompasses in the body, and that is fixed. So you can do that. Okay. And this is important because your computer will have a limited memory capacity. So your solver is limited by the memory capacity of the computer. So I know these days I've seen aero students talking about 50 million grid nodes in their problem. And to solve that, you need days, and you need a special computer as well. So you can't do that. You can't solve that using a day-to-day, even a high-end PC. You need a special a cluster of computers for that. And an inflation. So you know the inflation layer now, and inflation is a clustered set of grid nodes near a wall or near a boundary where you want to resolve that smoothly. Okay, so now that is a that is an inflation. Here, this is an inflation here. So that is to pick up the boundary layer. On the aerofoil, this is an inflation just to pick up the boundary layer. So make sure that when you have an inflation on a boundary layer, you make those grid nodes perpendicular to that boundary. Okay. Tets are good, but hexes are better. Okay, because, for example, in a boundary layer, the velocity, the gradients don't change rapidly along the wall, but it changes rapidly normal to the wall. So you need to have a higher resolution normal to the wall. Along the wall, don't worry much. So if you use global settings for inflation, all boundaries will be inflated, but you can, if you're not worried about the far field, you only pick up the layers that you want to have an inflation layer on. So you can specify the boundary for the inflation layer. So you must have seen this. So some of you, when you try to mesh your pipe, you might have seen inflation layers everywhere when you picked up the wrong boundary. Okay, so you had to pick up only the wall for the wall boundary layer in your exercise example. And then also you have what you call moving meshes. It is not in the context of this subject at this level, but when you look at when you see this presentation is available on Blackboard already. So pick up these click on these links and have a look at them. How a moving mesh operates. I'll give you a small introduction to it, how a moving mesh can operate. The classic example is the piston cylinder arrangement. So in a piston cylinder arrangement, in a piston and cylinder, what you mesh is the air volume. Is the air volume trapped within the cylinder. So if that is my piston, if that is my cylinder head rather, so the piston moves up and down like that. So your air volume expands and contracts like that. So it goes up and down like that. Okay. So there are two ways of accommodating this because it depends on time, doesn't it? There are two ways of accommodating the movement of the piston here. One is you can have grid nodes. You can have very high resolution grid nodes at a very, very high resolution, and you can keep on adding and removing layers from this volume. Okay, so for that you have to have a very large number of grid nodes, and every step, each time step you have a different number of grid nodes. So porting values from one set to the other is it takes a lot of time basically. And the other thing that you can do is you can have the same number of grid nodes, and you can change the size of the grid cells according to the movement of the piston. You will have the same number of grid nodes, but the size changes, like expands and compresses. Okay, so those are the two approaches that you can take. So this is just for the knowledge. You will not need this for your assignment. You are not doing moving meshes. Okay, now with that knowledge, see whether you can answer these questions in your leisure, mostly. Discuss advantages and limitations of CFD. So these are the types of questions that you will have to answer at the exam. Explain the geometry considerations you should make before creating a model. So when you see a geometry, you need to look at how you are going to create the mesh. So you need to create the mesh, you need to consider the geometry, the inlet, the outlet, the walls, the boundaries, etc. And we talked about the types of cells and meshes, so you need to know them now, at least by the time of the exam. And you need to know the meaning of mesh density and mesh quality. So all these words are there in your CFD package as well, and make it a habit that when you work onto screens, use one screen for the simulations for the CFD software, the other screen for tutorials, and have a Google open and check the meanings of the words that you encounter. Go to the ANSYS website, go to the CFX website, and have a look at what it all means. So that will give you the additional knowledge that you require. Also, there is a CFD help in the CFD help menu, so you can go to those pages, and there are theoretical explanations as well. So what we teach here are there. Okay. Also, identify mesh controls. So we just talked about mesh controls, right? Right. So today, from now on, we will talk about the theory. So we talked about meshes now. Now we will talk about theory. Theory in the sense how the theory behind the codes, theory behind the CFD codes, the maths behind it. Right. So we are looking at a fluid. You know that. So when you look at when you describe the physics in a fluid, you always have the conservation of mass. Okay. That means mass can neither be created nor destroyed. So mathematical representation of conservation of mass is the continuity equation. So I will show you how we write that in a minute. And then you have another equation, conservation of momentum. So that is the Newton's second law. Sum of external forces acting on a unit mass must be equal to the rate of change of linear momentum. So it's in 1D, that's F equals ma. Okay. So mathematical representation is known as a momentum equation. Okay. And then you have what you call the conservation of energy. Conservation of energy is basically the first law of thermodynamics. So the rate of change of energy within element equals within an element is equal to the net rate of heat entering an element plus the rate of work done in an element. So that means if you have an element, if you have a Q in and a Q out and a W out, so this Q in should be equal to the W out and the Q out. Q out includes waste as well. So that is the energy equation. So you don't have to derive the equations, but you need to know, or you need to understand what each term means, and you need to know what terms have to be neglected and what terms are important. Okay, then we talk about something called control volumes. Control volume. Now there are two ways of representing a fluid or analyzing a fluid. One is called a Lagrange Eulerian representation, and the other one is called a Lagrangian representation. Now consider a fluid element or a space fluid volume. Now what you have been doing so far is even when you take your pipe flow problem, you have a fixed volume, you have an inlet, and you have an outlet, and you consider this pipe to stay in the same space, and you considered the fluid to move in and move out of that space, and you didn't worry about the individual fluid particles inside. Okay? So you have a fixed inlet and a fixed outlet. Okay? So that is called a controlled volume, and you have an inlet and an outlet. Now that is one way of looking at it. Another way of looking at it is you can sit on those fluid particles and see what happens to those fluid particles. So they are moving. So they are moving at a certain velocity with respect to the space. Okay. So if you take the fluid particle, it will have a v velocity. Okay. And an ensemble of those particles, that means all those particles will create the flow field. Okay. So a good analogy to this is if you look at the flow on a motorway, the vehicles move along a motorway. So if you go on a bridge and watch those vehicles moving, you will see that okay, the vehicles are moving at 70 miles per hour. That is the speed, and then you can give a rate as well. This many vehicles pass this bridge at this point. And there what you are doing is you are looking at a moving flow whilst you are stationary. And there is another way of looking at it. You get in a car and drive it, and you read in the speedometer that's 70 miles per hour. Okay. There what you are doing is you are sitting in that moving vehicle, and you assess the speed or whatever is happening physically to that particular particle. So these are two angles of looking at it. So the first angle, when you have a fixed reference frame, and when you are looking at a volume, that is called the Eulerian. That is called the Eulerian representation of a fluid. And the second example, where you sit on the particles of the fluid, and when you analyze what is happening to the fluid with respect to that element, that particle, that is the Lagrangian representation of the fluid. Okay. So in in the first, in my left hand side, what you have is how you represent a fluid in an Eulerian form. So you have a fixed volume, you have a fixed volume, and the fluid moves in and out. In the Lagrangian form, you have a fluid volume, fixed volume, okay, and it will flow with the it will move with the fluid. Okay. So this is important. This Lagrangian representation is important when you have a chemical reaction. Okay. When you have a chemical reaction, you can work with a fluid particle and see what happens to the fluid particle. So you know what is happening to that fluid particle in terms of motion. You will also have to determine what happens to that fluid particle in terms of reaction. So, for example, you have a petrol particle moving, and at some point it will meet with oxygen, and there will be combustion. So, once it has caught fire, it will no longer be petrol or oxygen. It will be CO2 and H2. Okay, so for that you need to track that particle. You need to analyze that one. You need to track that particle. But you will still have carbon, hydrogen, and oxygen in that. Okay, so your composition changes, and your volume changes as well, and your speed changes too. But you can still track it. So, in Eulerian form, your integral equations are in conservation form, and also the differential equations are in conservation form. And in Lagrangian description, you will have your equation in a non-conservation form, and your differential equation also in non-conservation form. And for CFD, in your mesh, what you were doing was representing the fluid the equation in Eulerian form. But it is easier to derive momentum and energy equations in Lagrangian form. But the equations are the same, but it's a different representation when you go from Eulerian to Lagrangian form. And this is an introduction only of what is happening, but you are not supposed to derive these at the exam, but you need to appreciate what is going on. Okay, now we'll have a look at continuity equation. So, if that is your control volume, you have a net mass flow coming into the element, and there is a mass flow going out of the element. Okay. So your net mass flow in is rho u. Rho is the density, u is the velocity in that direction, in x direction. Dy dz is the area. Okay. And when it goes out of that element, your velocity has changed. Rho u times rho u over da by x times dx. So that is this is the change of velocity when it goes from that point to that point during along a distance dx. Yeah. So your velocity has changed, and but your area hasn't changed. Okay. So the mass flow out of the element is that, mass flow into the element is that. Yes. So your mass flow out of the element is equal to the mass flow is equal to, now this mass flow out is equal to the mass flow in plus any changes that it took that took place. Okay. So your net mass flow is only that. Okay. This one into dy dz. So your net mass flow is dabba rho u by dabba x times dx times dy dz. Dy dz is the area, dx is the length. In any direction, those are the that is in x direction. So you can write the same in x, y, in y and z directions also. So those are the mass flow rates, the change in mass flow in y and z direction. Now, therefore, your net mass flow can be written as adding that to that and that. So that, and you can see that dx, dy, dz are common. Therefore, you can take these out and add them together. And rho dx, dy, dz. Rho, if you say your rho is not changing, your rho dx, dy, dz is the mass. And time rate of mass change is dabba rho over dabba t, dx, dy, dz. And this time rate of change should be equal to the net mass flow rate. So that is your continuity equation. Okay, and you take that element to that part of the equation to the left hand side, and you can write your equation like that. So that is the net, that is the time rate of mass production or mass. That is the rate of change of mass. That is the spatial change. So this is the change in time. This is the change in space. Okay. And I take dx, dy, dz out because it's common, so it's a constant. And you can do the same. We can use the velocity vector. We can introduce the velocity vector into this equation. So velocity vector is u is the velocity, ui plus vj plus wk. So those are directional vectors. These are the individual velocity components, u, v, and w. I, j, k are the directional vectors. Okay. And when you take the del operator, dabba, which is nabla is equal to dabba by dabba x plus dabba by dabba y plus dabba by dabba z, which is, and if you use the del operator on the velocity vector, you will get dabba u by dabba x plus dabba v by dabba y plus dabba w by dabba z. Okay, that is that. You take the row out. So your conservation of mass, you can write it as dabba rho by dabba t plus nabla u, nabla rho u, nabla dot rho u. Okay, so this is writing the same equation in the vector form. And in the continuity equation, your dabba rho over dabba t is the time rate of mass change. So this is the change in time, and this is net mass flow rate, or that is the spatial change. This is in space, this is in time. So that's the same in the vector form as well. Dabba rho over dabba t is the time change, that is the spatial change. Okay. So for steady flows, so now that is your equation. For steady flows, there is no no change in mass rate in steady flows. What is coming in is going out. There is no change. Therefore, your delta rho over delta t becomes 0. There is no time change. There is no change in time. So your delta rho over delta t is 0 in your steady flows. So that is, so for steady flow, only that is true. And also, for incompressible flows, your rho doesn't change. Therefore, you can take the rho out. Okay. Therefore, your delta rho over delta t is 0, as well as your rho is constant. Therefore, you can take rho out, and your equation becomes delta u over delta x plus delta v over delta y plus delta w over delta z 0. Okay. And then we will look at the momentum equation. Momentum equation is in one dimension is F equals ma. So that means the acceleration of a body is governed by the mass, and the mass and the applied force. And there are forces which are pressure forces, viscous forces. On the body there will be gravity and electromagnetic forces on the body, and on the surfaces you have the pressure. You have the pressure, and you have stresses, normal stress and shear stress. Yeah. So if you take the right and left faces and so that is the x plane, top and bottom faces, that's the y plane, and front and back faces is the z plane. So your body forces applied on that is Fx, Fy and Fz, and then the pressures applied on the faces are so that is P on all the sides, but you have a spatial change in pressure in the x direction, in the y direction, and in the z direction as well. So in here, after dx after delta x after dx length, your pressure has changed from P to P plus delta P over delta x times delta x dx. Okay, so that is the same for all three directions. And the normal stresses. Okay, you have a normal stress in the xy plane as sigma xx, and when you go from 0 to delta dx distance, you will have sigma x plus change of sigma x due to distance times that distance. So that is sigma xx plus delta sigma xx over delta x times dx. Okay. So that is again true for x direction, y direction, and z direction. Okay. And the surface forces now, that's the normal stress, and then you also have the shear stress. So shear stresses are now on the normal to the x direction, you have two shear stress components which are again normal to each other, tau xy and tau xz. So those are the directional vectors. Therefore, you have two components on one face. That means on three directions you have 6 components. And when you add all of them together, you have your pressure force, you have a normal force, and you have your stress force. So this is only in the direction of x. only in the x direction, forces only in the x direction. You have your pressure force, you have your normal stress, and you have your shear stress applied in that direction. So that is not applied on the face, that is applied parallel to the along the face on the other faces. Okay. So you need to take all those into account when you derive the equation F equals ma equation in x direction. So in x direction, when you add all of them together, your forces is equal to the normal to the pressure force, normal stress rather, and the shear stress. Okay. So when you simplify them, you can write your total of forces are equal to the pressure force. Sorry, the force, the pressure force, and the normal stress and the shear stress. Okay. So do you call them the body force, the pressure gradient, and the stress tensor? This is called the stress tensor. This is due to stress. This is the pressure. This is the body force. Okay. So mass is fixed. Rho dx dy dz is fixed. And acceleration in x direction is du over dt. That is the speed divided by time. So that is called the substantive derivative. And then you can so we are trying to apply F equals ma. So if you look at this equation, right, that's your F. Yeah. So you are trying to equate this F to ma. Yeah. So you had your F here. Ma is the W or W t. That is your A. That is your M. Rho dx dy dz is the M. So that's your total momentum equation in x direction. So you can rearrange it and you can write it like this. Okay. So in here, that is your ma term. That is your those are the total of forces. Okay. So that's your body force. That's your pressure, force due to pressure. That's your stress tensor. In the stress tensor, you have the normal force, normal stress, and the shear stress. Yeah. And that is in the x direction only. You can write this in the y direction as well as in the z direction. So this is in the Lagrangian form. So if you wanted to change it to the Eulerian form, you can write rho du over dt as that. Therefore, your ma term is expanded to rho u over W t plus nabla rho u times u is equal to your forces, total of forces. So this is the momentum equation is in Eulerian form. Okay. So that is because in your acceleration term you have two acceleration elements. One is the local acceleration, and that is the advective acceleration. So local acceleration is the acceleration in time. So this is acceleration in space basically. Okay. So local acceleration, advective acceleration, body force, pressure gradient, and the stress tensor. And in the stress tensor you will have the normal stress and the shear stresses. Okay. So these are a couple of examples for local acceleration and advective acceleration. For local acceleration, you can use this the example of opening a valve or a tap, or for advective acceleration, you can look at the change of flow direction and change in the pipe diameter. So the second example is for a tidal estuary. So you have local acceleration here, and advective acceleration is in the estuary. This is due to the change in space. Yeah. This is acceleration due to time, and this is acceleration or deceleration due to change in space. Yeah. Because of the change in size, there is acceleration and deceleration, right? So, and also due to if your mass flow rate changes, then you will have time change. So that is a local acceleration. So you can write the same equations in y direction as well as in z direction. So you just change the directional notation to obtain these two once you have written the x direction equation. Okay. So momentum equation, the full momentum equation is the addition of all three equations. Yes. So in all those terms, all those equations, you have the same thing: local acceleration, advective acceleration, body force, pressure gradient, and the stress. Yeah. Stress is normal and normal stress and shear stress. So normal stress one component, shear stress two components. Right? Usually you call this the stress tensor. So in the stress tensor, you have the normal stress as well as the shear stresses. Questions? Any questions? Didn't understand a word, yeah? Okay. I'm sure you're fine, yeah? Okay. So, so we derived these equations based on a stationary fluid element, and momentum equation we derived this based on a moving fluid element, and this moving, we transformed that momentum equation from non-conservation term to the conservation form. Okay. And look at how these terms change with one another. Have a look at this, try to understand this applied onto a element. Okay. And then we will replace the terms, stress terms, with an expression, and we will write the Navier-Stokes equation. Okay. So if you look at this equation, you have your stress term here, yeah. So that's your normal stress, that's your shear stresses, right? And in the Navier-Stokes equation, in the stress terms, these are sigma xx, sigma yy, sigma z. Now these are normal stresses. Normal stresses can be written in terms of velocity gradients for Newtonian fluids. Newtonian fluids are fluids that will obey the laws of Newton's laws. Okay. For non-Newtonian fluids, we can't write the same thing. Okay. So your normal stresses can be replaced with the with velocity gradients. So, and this can be, now this element is actually nabla.u. So therefore we can add them. We can replace this replace the equation using mu times 2w over wx minus 2/3 of nabla dot u. Right? And then you can write your tau xy, the shear stresses, in the same fashion as velocity gradients, and therefore you can replace your momentum equation by substituting those velocity those gradients with what you wrote earlier. So you replace your stress components with the velocity gradients. Okay, so with that you can write your therefore you substitute sigma xx, tau yx, and tau zx in the right hand side of this equation with what you just wrote before, and that's your momentum equation. Now this equation is called the Navier-Stokes equation. This is the Navier-Stokes equation. Okay. And it has a mu term, which is the dynamic viscosity. Okay. So we are rearranging this equation. Okay. So, and W squared over W x comes from here. That one comes from there. The W squared u over W squared, and this one comes from here, W squared u over W z squared, and then that term comes from these two. That mu is those three mu's, and W over W x times W over W x comes from here, and y comes from there, and these terms W comes from here, and that is called nabla dot u. So that is my complete Navier-Stokes equations. Okay, and you can simplify these two as well to 1/3. Right, that finishes the lecture for today. Thank you for listening. Read this one before you come to the next lecture. We will start from here. Okay, thank you.